Okay, so we got into galvanic cells last time. And remember, galvanic cells have a few different parts we talked about. On one side is the anode part of the galvanic cell. That is where oxidation occurs. On the other side is the cathode side. Bless you. And that is where reduction occurs. Remember, it is really just an oxidation reduction reaction happening. So on one side here, we would have a solid electrode. Say something like zinc. And in the solution, we would have zinc ions floating around, obviously, as well a spectator ion like a sulfate, maybe a nitrate or something like that. We have a wire that kind of connects both sides, it goes through usually a voltage type of meter. And on the other side, again, we have our cathode, which is also a solid in there, something like copper. And in the solution, we would have copper ions also with a spectator ion, maybe like a sodium, a nitrate. Usually, we also have a salt bridge that kind of connects both of the sort of components. The salt bridge usually contains some type of salt, like the example I think we saw in the picture, potassium chloride. And the function of the salt bridge, as we talked about, is essentially to really keep the galvanic cell sort of running functionally. It also prevents the buildup of sort of the wrong charge on each side. So what happens, right, is as these zinc guys lose electrons, those electrons go through the wire and go towards the cathode side. There's sort of a potential difference, more positive side on the cathode, that's going to kind of pull those electrons to the other side. When the zinc loses electrons, it then actually goes for a swim out into the solution as an ion. Those electrons that come down the other side actually combine with the ions in the solution, and that causes, in this example here, the copper to come out of solution. So the salt bridge allows really for the buildup of, or not the buildup of the wrong charge. As I mentioned before, if you were sort of missing the salt bridge in this setup, what you would essentially have over here happening is a buildup of positive charge, which is not really good because that's going to really stop the flow of electrons as they are negatively charged. So they're not going to want to really go to the other side. You would also have, if you didn't have the salt bridge, a buildup of negative charge over on the cathode side, which would also sort of prohibit the electrons from coming that way. So again, that is why we saw in the picture the chloride, the negative guy, was coming this way to kind of cut down that positive buildup. The positive ion was coming this way to kind of cut down on the buildup of the negative sort of charge. We could calculate the cell potential or cell voltage by taking E of the cathode minus E of the anode. And remember that we could use the SRP values that you can find in a table. That is the standard reduction potential values. They're all written as reduction reactions. So as we talked about, since really the anode side here is always an oxidation reaction, technically speaking, you do have to kind of reverse one of the reactions that you find in that table because it's really written backwards. And you can do one of two things. If you reverse the reaction, you can change the sign that you see in the table for it to be the correct sign. And if you do that, as we talked about, you really should add instead of subtract. So if you decide yourself that you want to change the sign, you change the sign on the anode, you should add. Now, if you don't want to worry about changing the sign, you just simply just want to grab the value from the table, then you should subtract, as we talked about last time. Really, the purpose of the subtraction is to change the sign on the anode. So it'll just kind of do it for you without you having to worry about should I change the sign or not change the sign. You can just grab the value from the table and then you should be in shape. We also related this to delta G. Delta G equals minus NFE. And that is our Gibbs free energy. And again, Remember that a negative delta G means reaction is spontaneous. And we really achieve a negative delta G by having a positive E of the cell. So a positive E of the cell will give us a negative delta G. F is Faraday's constant, 96,500. And N is the number of moles. And remember, that's the balanced number of moles that really is lost by the person being oxidized and gained by the person being reduced. We also saw a relationship that E of the cell is equal to RTNF natural log of K. And again, this relates our equilibrium constant to our E of the cell. As we talked about, really all three of those things should sort of agree with each other. If you have a positive E of the cell, that means that the reaction is spontaneous. That gives you a negative delta G, which tells you it's spontaneous. And that means you should really have more products than reactants at equilibrium. And if you're solving for something for the equilibrium constant, you should have a large value of K. And vice versa, if you have a negative value for E of the cell, that should mean the reaction is going to be non-spontaneous, as that would lead to a positive G value. And that would mean you would mainly have reactants versus products at equilibrium. And if you calculate something like K, then obviously you should have more of a small value K. So again, all those things should agree with each other. Any questions on any of that there? All right, so let's try one here again. What is the equilibrium constant for the following reaction? And those are some SRP values you can find from the table. So why don't you take a moment there and calculate it up and see what you come up with. Okay, so let's take a look at this. So obviously here we're looking for the equilibrium constant. So E of the cell, little RT, NF, natural log of K is our formula here. So we'll start with E of the cell, which is our cathode. And again, I'm going to go minus my anode, so I'm not going to change any signs. I do want to identify which one is my cathode. And in this particular case, my cathode is the iron is my cathode. A reminder that this would be a situation where you would not go with the more positive one because you're actually given an equation. And in the equation here, we see the iron going from +2 to 0, which means that it is being reduced, while the silver here is going from 0 to +1 and being oxidized. So again, a reminder, you do need to look at the equation if you're given it and figure out what is being oxidized, what is being reduced to determine cathode and anode. You only use the more positive one if you're not given any information basically about how it's happening. So with that being said, that means that we're actually going to go negative 0.44 volts. And again, I'm not going to change the sign. So minus 0.80 volts. And that's going to get me here a negative 1.24 volts in this particular case. My N in this case is going to be 2, as that is iron 2, which means it will be reduced by 2 electrons here. And the silver, since there are 2 silvers, each one will lose an electron and give us 2 in the balanced equation. And again, that is where we get our N is equal to 2. We again do not add them together or anything like that, so it's just 2 in this case. Temperature 298 on the conversion here. I think that's almost all we need, so I'll go negative 1.24 volts is going to be equal to my R. Remember, this is the one with the energy, 8.314 joules per Kelvin per mole. Our temperature of 298 Kelvin divided by our N, which is 2 moles, and our 96,500 joules per volt per mole times the natural log of K. Cleaning up a little bit on the right-hand side there, 8.314 times 298 divided by 2 and divided by 96,500 gets me something like 0.012837. natural log of K minus 1.24 volts. Obviously, we're going to divide that to the other side. So we'll do that, and that will get us negative 96.59 equals the natural log of K. To get rid of the natural log on both sides, you're going to E both sides. When you do so, the natural log goes away on that side, and it finally gets us a K value here of, looks like maybe 1.1 times 10 to the minus 42 in this particular case. Any questions on that? Again, with some rounding, depending on where you round, you may get a slightly different front number, especially when you take the E of both sides. Any questions on that there? All these things do sort of make sense. We ended up with a negative E of the cell, which means this reaction really should be non-spontaneous. Although we didn't calculate it, if we did, we would end up with a positive value for G, which tells us it's non-spontaneous, and we should have just reactants mainly. And because of that, we should have a small value of K, which we do in this case as well. So again, like I said, those things should sort of agree with each other when you sort of calculate. Any questions on that? Yeah. All right, then let's talk a little bit about the effect of concentration on the cell voltage. Now, as we saw before in sort of the thermodynamics chapter, we have our delta G under non-standard conditions, or delta G under standard conditions, and we can relate that to sort of our E of the cell. And that gives us sort of this equation right here, which is the Nernst equation. And the Nernst equation is really one where you use when you have some type of non-standard conditions sort of happening. So it's very similar to our delta G. Remember, pretty much standard conditions, 1 atmosphere for pressures, 1 molar for concentration. So if you come across a problem where maybe you have pressures that are not 1 atmosphere, maybe you got concentrations that are not 1 molar, that's going to be sort of a Nernst situation in a non-standard conditions. You could kind of think of that's sort of what that E stands for. It's kind of the E of the cell under non-standard conditions. Again, that's going to be our cathode minus our anode. The rest of these guys are pretty much our normal things that we just used. That's our gas constant, our 8.314 version. Obviously, that's our temperature in Kelvin. That's our moles. That's our Faraday's constant. And here we have the natural log of Q. And Q, as we've seen many times, calculated the same way as you would do K against our products over our reactants. So we would use this equation again in a sort of non-standard condition. If you wanted to at 25 degrees, they do reduce down to these versions of the Nernst equation, but much like we talked about, I think with the previous one, if you don't want to worry about those two equations, just remember the Nernst equation, just put all the numbers in and everything will come out basically the same. So you don't have to necessarily reduce them down. But if you did at 25 degrees, that's what they would reduce down to. By the way, this is where we get our previous equation that we used because at equilibrium, in case you forget the previous equation, at equilibrium, E would equal 0 and Q would equal K, which would turn the Nernst equation to 0 is equal to E naught minus RT NF natural log of K. Taking this entire thing and adding it to the other side gives us our equation that we just used a second ago. And that's how you could get to sort of the other equation from the Nernst equation if you want. Just set those guys equal to 0 and then solve for it as well. Any questions on that there? All right, so let's take a look at one here and see how it all works, I think. There we go. Will the following reaction occur spontaneously at 25 degrees if you have an iron 2 concentration of 0.6 and a cadmium concentration of 0.01 molar? And again, there's some SRP values. So take a few moments there, calculate it up, and see what you... Okay, let's take a look. So once again here, we're looking to see if this reaction is going to be spontaneous. This is a hint that we need to use the Nernst equation. This is sort of under non-standard conditions, as again, standard conditions would be 1 molar for all the concentrations. And here, obviously, they're not 1 molar. So we'll use our E is equal to our E naught minus our RT NF natural log of Q. So we'll start with our E of the cell, which is this guy here. And again, I'm going to do cathode minus anode. I'm not going to change the sign. Once again, I am given an equation, so I do want to look at it, and I see again the iron going from +2 to 0. So again, becoming more negative as you travel down sort of the number line there. It's going in that direction towards negative. And that means that it is, again, in this case, not based on these numbers, but it is the iron that's going to be our cathode, and our cadmium, in this case, would be our anode. Any questions on that there? So putting in our values for that, that's going to get us then negative 0.44 volts minus a minus 0.4 volts. And that will get us here negative 0.44 minus 0.4, a negative 0.04 volts. So under standard conditions, our reaction here is non-spontaneous, as we have a negative delta G, negative delta E, or negative E, which would give us a positive delta G, so we know it's non-spontaneous. So what we're going to look at is whether or not it may become spontaneous under these conditions. We have our temperature, which is 298 Kelvin. Our N in this case is also going to be 2, as we have, again, like previously, our iron 2. And in the case of cadmium, we have our cadmium given up 2 electrons. So again, N in this case is going to be 2. And I think almost that's everything we need. We do need to calculate Q. Q in this case would be the concentration of cadmium divided by the concentration of iron 2. Again, these guys here are solid, so they would not be included. Also, why you're only given, obviously, 2 concentrations. So that would be, in this case, 0.01 divided by 0.6 in this case. So sort of putting it all together here, we got our E is equal to our negative 0.04 volts minus our R, which is 8.314 joules per Kelvin per mole, our temperature of 298 divided by our N of 2 and divided by our constant 96,500 and natural log basically 0.01 divided by 0.6. So getting some numbers here. Maybe we'll clear up to the right of our subtract. We're going to take 0.01 divided by 0.6. I'm going to take the natural log of it. I am then going to multiply it by 8.314. I'm going to multiply it by 298. I'm going to divide it by 2 and then divide it by 96,500. That is going to yield me negative 0.04 volts minus a minus 0.0525597. And now to get my E of my cell here, minus 0.04 minus my answer, gonna get me basically a 0.013 volts in this case. And that is a positive voltage, not a lot, but that is some type of positive voltage. And basically under these conditions, it would be spontaneous, as we did achieve sort of a positive voltage in this case. Any questions on that there? Are you talking about these bottom ones? Yeah, so these bottom ones are really the Nernst equation. They're just a kind of reduced down version of the Nernst equation. At 25 degrees, basically the R, the T, and the F are kind of like constants. And they're both perfectly the same in the sense you could use either one if you want to use them. It is 25 degrees. If you use the natural log, you do have to use 0.0257 up on top. But if you want to use kind of the base log 10, you can use the 0.0592. So they will all three of these equations, technically speaking, give you the same answer. Now, I will say, as I mentioned before, sometimes depending on rounding, especially if you're doing like the inverse log or something like that, you might get a slightly different answer depending on where you rounded, but you should get pretty much the same answer regardless. So if you don't want to worry about these two equations on the bottom, like I mentioned earlier, I wouldn't worry about it. I would just plug everything into the Nernst equation and you should be in good shape for them. Other questions? Okay. So again, Nernst equation is what we use in a non-standard condition. And in this case, as you can see, we had some non-standard concentrations. You could also potentially have some non-standard pressures as well. All right, so one last one here for the following. Forget the balancing part. Just calculate E and K for this one here. Okay, let's take a look. So again here, we're looking for E and K. So as I mentioned before, if you can't remember that equation, but you can remember the Nernst equation. Again, you could kind of derive it from it. Again, at equilibrium, which obviously we would be at since we're looking for the equilibrium constant here. E would equal 0 and Q would equal K. Again, that gets you 0 is equal to E naught minus RT NF natural log of K. Taking this entire thing basically and moving it to the other side gives you our E is equal to our RT NF natural log of K. So once again here, we do need to calculate E of the cell, which is going to be our cathode minus our anode. So we are given an equation here. So again, we do want to look at it here. Chromium plus 2, it's a plus 3. So that is becoming more positive and getting oxidized. That would mean our chromium would be our anode, and this guy here would be our cathode. If you're not sure, that's like a -2, that's a 12, that's a 10. That's something like a 2.5 there for the sulfur on the left. That's a -2, -6, -4, and a +2 over here. So the sulfur going from 2.5 to 2, slightly moving in the reduction sort of negative way, and that would be our cathode. So popping in our numbers here, and again, I'm not going to change the sign, so we're going to go 0.17 minus a minus 0.50 volts, and that's going to get us here minus 0.17 minus a minus 0.5. That looks like a 0.67 volts. So that's a positive voltage, which means we should expect this reaction to be spontaneous. That also means we should hopefully expect probably a larger value for K when we do solve for it. So let's see if that is the case. We're going to go 0.67 volts equals our R, 8.314, 298. Our N in this case, if we balance it, we do need to pop a 2 through here, and N would equal 2 in this case. And that's going to give us 2 moles and 96,500 natural log of K. Again, cleaning up the right-hand side there. 8.314 times 298 divided by 2 divided by 96.5. Going to get us a 0.012837 equals 0.67 natural log of K. Obviously, we're going to divide first. So 0.67 divided by that. Going to hit us a natural log of K equals about a 52.19. Going to E both sides there. And that goes away. K about 4.6 times 10 to the 22. which I would say would qualify as a large value of K, which again would go good with our positive value of E and our probably negative value of delta G, which means this reaction should be spontaneous. Yeah. Any questions on any of those calculations there? All right, I think that's a good place to lay it up for today.